Okay, cool. You
Okay,
can see.
can you see the slides now?
Yeah, you can. Yeah, we can see it. You can start thinking.
Okay, sounds good. Hello everyone. I'm glad to present our recent research at NVIDIA Research in the Singapore lab. So recently we've been working on the combination of physical AI and efficient AI, where efficient AI provides more efficiency for physical AI, and physical AI drives new demand for efficient AI. So this is the agenda for today's talk. How do we make visual generations more efficient? Because visual generation is the major part of the recent video world foundation models, world action models. So I'm going to talk about three techniques. The first technique is how to reduce the number of tokens using the deep compression tokenizer. And the second part is using efficient model architecture to accelerate video generation from ON square softmax attention to ON linear attention. I will talk about the Sana video generator. And for the last, I will talk about how to generate image and videos using fewer steps, from 50 steps to a single step. So we'll start with the first technique, how to reduce the number of tokens by efficient tokenizer. So why high compression ratio VAE matters? Because diffusion model scales quadratically with the number of tokens due to the softmax attention. And also the high compression variational autoencoder can represent images using fewer local latent tokens. We hope to preserve the quality while reducing the sequence length. And thirdly, it will unlock faster generation and better GPU efficiency. So this is a quick overview of high compression ratio VAE. Previously, we encode the image with a lot of tokens, which is slow and high cost. Now we want to enable high compression VAE to use fewer tokens, but still be able to fully recover the original image very well. Therefore, we built this project called DC Cosmos Tokenizer. This is the visualization of the reconstruction performance. So the first category is the high frequency videos. The second category is small faces. Those are real world use cases. And the third one is ultra motion. And the last one is ultra 4K. So the left column is the original video, and the right column is the reconstructed video. We can see using the DC Cosmos tokenizer, we can have a pretty high compression ratio without uh, compromising the reconstruction quality. And on the right-hand side is showing the performance on the reconstruction on different scenarios, high frequency, small phases, ultra motion, ultra 4K, comparing the DC Cosmos tokenizer with the one tokenizer LTX Cosmos tokenizer. And the idea is to have a bypass branch to explicitly reconstruct the downsample process and have a progressive reconstruction training pipeline. On top of the DC tokenizer, we developed this DC Gen, post-training diffusion acceleration with deeply compressed latent space to enable fast tokenizer adaptation and post-training acceleration. So the use case is that you want to have a pre-trained DIT model. Okay, we don't want to waste or retrain the weight from scratch, but we want to adapt the tokenizer to be the deep compression tokenizer so that we can save the compute and be able to reuse the majority of the weights in the DIT. For example, you have a one model, you want to accelerate one without having to retrain it. And here, the left-hand side is showing the idea here. We can maintain the same DIT blocks in green, but we change the tokenizer from the original VAE into the DC deep compression tokenizer. And we fine-tune this patch embedding layer, okay? And also the inherit the DIT layer. So we generate fewer tokens. Previously, there's a lot of token, now it's fewer token. and we plug in the output head and to generate fewer tokens to reconstruct the original image. Using this simple approach, we can drastically reduce the number of tokens, therefore the generation speed. Previously, it took 27 minutes to generate one video. Now it takes only 3.6 minutes to generate a single video. And you're comparing the quality, they are pretty much the same. Well, this is the training cost measured in GPU days. Since this is adaptation approach, you don't have to train DIT. So the adaptation speed is quite fast. It's three orders of magnitude lower compute cost than training a model from scratch. So here is comparing the quality generation performance of the DC Cosmos tokenizer. Um, the left column is the DC Cosmos tokenizer. The right column is the one VAE. We can see for this car will suddenly disappear and rotate, but on the left-hand side is pretty stable. And on the top, the robot arm will change the shape suddenly, but with DC Cosmos tokenizer, the robot arm is still maintaining pretty good physics. On the PyBench, DC Cosmos tokenizer is showing pretty good score across different quality benchmarks. Okay, so that's the first step, reduce the number of tokens using the DC deep compression DC compression deep compression Cosmos tokenizer. And for the second technique, I'm going to talk about efficient model architectures. We know that the diffusion model require ON square computation complexity, where the more tokens, the more compute. For images, if you have high resolution image generation, the number of tokens actually grows quadratically with the resolution. So actually, the number of the compute will grow ON to the power of 4 with the resolution. That's a lot. Well, linear attention is quite popularly used in language model. Hybrid attention, Mamba, those are quite popular in language model. What about in video generation? Does that provide enough capacity? And how do we model those long image video generation, high resolution image generation, and long video generation using the limited capacity provided by linear attention? So I'm going to introduce this Sana project for efficient video generation pipeline. So Sana is a video generator we trained from scratch using only 64 H100 GPUs for 2 weeks. We have quite a limited resource. How do we train it with so few GPU resources? So the architecture is purely linear attention based. So first of all, we chop the long video as a sequence of chunks. Each chunk is about 1 second. And between the chunks is using the autoregressive model, generating the frames chunk by chunk. So that's between the chunks, fully autoregressive. Each chunk is generated conditioned on all the previous chunks. Well, within the chunk, we are using diffusion denoising. We use multiple steps from random noise to high quality video frames. And we enable the efficient diffusion by optimizing the diffusion model for long video generation, even on consumer GPUs. And here, the core technique is to use linear attention wherever possible. So here is comparing the softmax attention and the linear attention. Softmax attention, the computation complexity is ON squared D, where N is the number of tokens, while the D is the hidden dimension. Well, linear attention, the computation complexity is OND square, where N is the number of tokens, while D is the hidden dimension. As we can see here, we are changing the sequence. Previously, we are doing the QK first, and the computation complexity is O(n) squared d. N is pretty large as the resolution go large, and as the sequence length go large. Well, here is O(n)d square on the right-hand side. So using the linear attention, we can compare the speed up. So here, the x-axis is different resolution from 192p to 720p. The latency speed up is quite significant. 2x speed up for 480p and 4x latency speed up for 720p. And here, the second advantage of using linear attention is the constant KV cache. Using a fixed memory footprint for seamless chunk by chunk generation. So originally using softmax attention, the KV cache grows linearly. The more you generate, the longer you generate, the more it takes for the KV cache. And the size of the memory grows O(n) according to the sequence length. But using linear attention, we can use a fixed cache size to deal with the memory. So the more you generate, here is the number of seconds on the right-hand side. The more you generate, the more you save. Here, the block linear attention is taking a constant size of memory, which is about 7.2 gigabyte of memory, which fits very well into a consumer GPU. While for softmax attention, the memory will grow quadratically. It will soon get run out of memory when the video length is more than a minute. A natural problem for this constant KV cache size is the capacity limitation. How do we generate long video and have enough capacity? We solve this problem by adding this temporal convolution to deal with the drawback of the linear attention. Okay, we want to enhance the local information extraction capability of linear attention by using convolution. The key observation is that the video generation require very long range dependency to have a global context. Linear attention is very good at it. However, linear attention is weak at local temporal continuity to model the local characteristic. But we know that temporal convolution is very good at modeling this local information. So we want to explicitly model the local temporal pattern using the convolution. So on the right-hand side, we are just doing pixel-wise cross-frame relationship modeling using linear attention, using the convolution. So we are convolving across different frames in a pixel-wise manner. So it's a 1D conv over time temporal convolution. Okay, by combining those techniques together, we deliver this SANA video model with pretty good accuracy. So the benchmark is SANA video over other methods on a 480p video generation. So the latency is the fastest across different models. Speed up is about 8 times. It's a 2 billion parameter model. It's bigger than other models, but being even faster. It's showing that the model size doesn't represent the speed. Even larger model, if you can design the architecture properly, it can run even faster, about 2 times faster or even 8 times faster than other models. So these are the evaluation scores: total score, quality score, and semantic score. And the higher the resolution, the larger the speed up. On a 720p video generation, it can be even about 16 times faster than the baseline methods. And here are some of the generated video quality. A command with an ostrich and a cow running across the field. And here are applying SANA for physical AI simulation to generate robot data, robot arm data to augment the data generation for physical AI applications. And recently, we also extended the Sana project to build this Sana world model, the controllable world model. You can go with different degrees, go forward, backward, left, and right, and tilt and rotate. So we can accurately model the world across different scenarios. And how do we achieve it? So the input basically consists of what you want to generate. Consists of the camera trajectory, the path, the angles, the motion, and give it the first frame, the starting image, and give it a text prompt. For example, if your car drives down a hillside town street. So by combining these three inputs, we feed it to the Sana world model, which actually have two steps. The first step is coarse grained generation to generate the big picture, understand the scene, capture the global layout and motion, and align precisely with the input trajectory. Again, it's using the hybrid linear attention using several gated delta net blocks with efficient state space sampling, supporting long range dependency modeling with linear complexity. So this architecture has fast generation and capture global layout and motion. It's coarse grained, but it's complete and it has a high precision trajectory alignment. With the second stage, we have a refiner to further support the finer generation. So it can refine the details and fix the artifacts to produce high quality, temporally consistent videos. It can enhance the details and improve the temporal consistency and remove artifacts. So we find this two-stage generation pipeline is better than one stage. It's faster and more efficient. And finally, it will just output the high quality video that is trajectory aligned and also temporally consistent. So this is the analysis of Sana world model. So efficiency-wise, the Sana world model has two parts. The VAE part consists of a 4 second, and the DIT part is about 21 minutes. Well, we can reduce the time for DIT by distilling it to only 4 steps that reduce from 21 minutes to 43 seconds. And finally, we can apply the attention sync, which was first proposed in our streaming LLM paper, which is showing the first token or the first frame is very crucial to maintain the dynamics of the attention. While for long generation, it's very safe to use a windowed attention to model the remaining of the KV cache. So in short, just the sync token, the sync frame, plus the windowed attention, that works perfectly. So that further brings down the size of the KV cache and also the generation speed from 48 seconds to 34 seconds. So those are the results on H100. And the Sana world model is also deployable on a single 5090, a consumer GPU. So without attention sync, it will run out of memory because the KV cache will grow. Well, plus the attention sync, you can generate a video that can fit the 5090 GPU. Even quantizing that to NVIP4 can reduce the latency to 34 seconds. And the right-hand side is showing the latency and GPU memory comparison on H100, comparing the hybrid GDN softmax attention versus softmax only versus cumulative linear approach. So this is about 1.8 times faster compared with baseline methods And the longer the video you generate, the more memory you can save. And here are some of the results. First one is showing a sports car driving through a town with mountains. Here are the controller going forward, going right. Similarly, on the right-hand side, you can move in this virtual world by controlling it by yourself using 6 degrees of freedom. And using what is the relationship between this world model and the robotics application? What is the real world application? So we built this model called 4Act, which can make coffees. So it's using the Sana image generation model to predict what is going to happen in the next frame. For example, the next frame should be holding this capsule. And then it's going to achieve that goal. Then it's going to predict the next goal for the middle camera. It's going to hold, it's going to open the space here. Okay, then achieved it. And the next goal would be put the capsule in the compartment. And then close the cabinet. So the first row of it is showing the predicted image by Sana to guide the next step. For example, here is showing the next step is to put the cup in the coffee machine. And then finally it achieves it. So here Sana acts as a world model to predict what is going to happen next, and as a world simulator to guide the robot to think what is going to happen next as a visual chain of thought. And finally, the coffee machine is making coffee. And notice here we are playing the video at only 1x speed. Many of the robot videos, sometimes you can see is 4x or 5x speed, but due to the Sana Sana is so fast, we can achieve everything we don't have to fast forward. Okay, so on the left-hand side, let's go through the details of the 4Act, which is to appear at CVPR in a few days. So it combines the current observation and a substack instruction as the input, and then it's going to use Sana to generate a high-resolution image for take high-resolution input for fine details and subtle movements. It adopts the deep compression autoencoder, which we introduced just now, for 32x compression ratio to take the input image, and then using linear DIT to generate the visual chain of thought, which has ON complexity, linear attention. And then we can cat noise tokens with condition tokens to serve as the input. Overall, this 4Act model has 1.6 billion parameters for linear DIT and Gemma 2B for the small language model. And for long video generation, we also worked on how to build interactive video generation models. For example, every 10 seconds, we are going to change the prompt and change the video, and then how to generate the video according to new prompt. So the idea is to achieve real time 20 frames per second on each 100 interactive video generation and long video generation. And here the idea is to enable streaming long tuning, okay, to train long and test long. And then adding frame sync plus short windowed attention. Okay, so first token is very crucial. We should always pin them in the KV cache, and later we can use windowed attention. And finally, we can apply KV recache for prompt switching. When you are adding a new prompt, you want to redo the KV cache. So by combining them together, we also build this NVIP4 infrastructure to enable long video generation by being 2x faster. So left-hand side is BF16 reference baseline. The right-hand side is NVIP4, same quality, 2x faster. And the training is about 2.15 times faster. Inference is about 1.84 times faster. And it's running 45 frames per second. You can generate multi-shot stories. For example, finding a key under the shadow. And everything is done by this long live that support multi-shot video generation, not just one shot, but it's going to generate, this is the first shot, and this is the second shot. This is the third shot and the fourth shot. Okay, so far we talk about token compression, efficient architecture, and finally let's talk about how to generate using fewer steps. So we propose this idea called any flow for any step video diffusion model with on-policy flow map distillation. So the inference cost is proportional to the number of tokens times the number of sampling steps. Previously, the token compression technique reduced the number of tokens, while any flow can reduce the number of sampling steps. Previously, the forward consistency training approach will learn to map from a random time frame, like time t to time 0. Different from this consistency distillation, any flow target learning any two time steps from ZT to ZR to achieve faster inference with adaptive budget, as shown on the right-hand side. Rather from T to 0, it is from T1 to T2. So the generation quality will be very consistent across different time steps. So as we reduce the time sampling steps, the model performance remains quite well. This is different from consistency distillation, where it's going to be working at only a certain time step. For example, it only works at 4 steps. At 2 steps or more steps, the model quality will collapse. On the right-hand side is showing 4 steps, 16 steps, and 32 steps.
In the middle.
And the teacher model is a consistent
Hi,
distillation.
Professor Han. Can you try to share your screen?
I'm sharing the screen. Is it disappeared?
Oh yeah, we can see it now. Yeah, it's working.
Oh, okay.
Thank you. Yeah,
Oh,
please
okay, that's
continue.
good. Okay, I'm almost done. And the second, and here we are comparing the speed using the any flow distillation. It's about 15.9 times speed up. Well, the first row is 114B, and the second row is the any flow 114B. Previously, it takes 8 minutes to generate the video. Now it takes only half a minute to generate the video, from 50 sampling steps to only 4 sampling steps. Okay, in conclusion, we talk about 3 techniques for faster visual generation by reducing the number of tokens using deep compression autoencoder and using efficient model architecture using linear attention for the SANA video generation model and the SANA word model. Finally, using any step, using the any flow distillation approach to reduce the number of sampling steps. And finally, we are building a new research lab at NVIDIA in Singapore. So we have a great team over there. We are hiring. Welcome to join us. All right, that's all for my presentation.